And okay, so lecture 8, the slides that were posted, it does include the slides that we did not finish for USCS. So just letting you know, there's some overlap in that. We were on an example problem for the USCS section. What does USCS stand for? United States of America. That's right. No, Unified Soil Classification System. Unified meaning like they actually use this in outside of the United States. So AASHTO, which is American Association of State Highways, something, something, something. That's primarily used in the United States, but USCS is like a global international thing. So the Unified Soil Classification System. And it's that lovely, beautiful flow chart, which I said you either love or hate. So we are going to be finishing that one today and then going over the soil classification part 2, which is the AASHTO. So there are some similarities to them, but there are a lot of differences. So we'll highlight those along the way. The quiz number 4 will be posted shortly after class. So that will be on soil classification, just on these lectures. The lab number 3, which everyone should have completed, which is the sieve analysis, that lab report will be due next week. So for this next chunk, we will have labs due 1 week following after. I'll provide comments and start grading your lab 2 as quickly as possible so you can make adjustments for lab 3. Any questions on schedule where we're at so far? Sweet. All right, so sticking around in soil classification, so these 2 textbooks, I don't think I posted the ASTMs yet, but you can just Google search either AASHTO or USCS and download those ASTMs for free on UNF Wi-Fi. So we end the day with this, and hopefully you've been just thinking about this flow chart in your dreams and stuff, because it took me a long time to make it. So I really appreciate it if you remembered it forever. But this flow chart is the USCS flow for the symbols. So you can see the bottom, this is the group symbols. We start at the top, and then we finished with 1 example. We'll go over 2 more examples, but this is kind of the overview of the USCS. The first symbol is based off of the grain size. So we primarily either have coarse grained or fine grain. And then the second symbol is based off of gradation if we have a coarse grain soil, and then plasticity if we have a fine grain soil. So for gradation, we look at the gradation curve and calculating the CC and the CU, which is the coefficient of uniformity and the coefficient of curvature. For the fine grain, what chart do we use? What's the name of that dude? It's a Casagrande chart or the Atterberg chart. I don't remember which one it is, but it's the old one that was developed in the 1940s. And that's the chart we use, where we take the liquid limit on the x-axis and then the plastic index on the y-axis, and we find the corresponding part in the region that the chart is in. So I want to think about like what these symbols physically mean, because if you get a report and it says like SM on it, what does it like physically mean? So like if we have an SM, that means the majority of the particle sizes are going to be what? Yeah, it'll be sand. The majority of the particle will be sand-sized particles, which is something between number 4 and the number 200 sieve. So the majority, meaning 50% or greater.
So the majority is always the first letter?
Yes. Mm-hmm. Yeah, the majority is always the first letter, 50% or greater. But it's important to remember, like, it's just the majority. So there can still be gravel, there can still be clay in it, but it's just the majority. So with this, the fine particles in an SM will behave like a what? So what is the M? Yeah, so this is what it's saying. It's like, all right, an SM type gradation or classified soil will be majority sand particles, but the fines that are in it are enough that make it have behavior like a silt in it. So this would be behaving like, come on, like, dude, what's up with this? Like a silt. So let's say like something like this. So how would we describe a GP? So the majority of the gravel, or the majority of the particles, will be the size of a gravel. which means it's greater than the number 4 sieve. I'll just go ahead and put this. So between number 4 and the number 200 sieve. And then the soil is non-plastic, so meaning it won't stick together. So the gradation controls more so than the plasticity, so there's not a large amount of fines in it. And it is what type of gradation? Yeah, poorly graded. And so we find this gradation based off of the CC and the CU, which are those indices from our grain size distribution. And remember, like it's harder to become well graded. Like most of them are going to be poorly graded. So like cream of the crop is well graded. So that's why there's these cases where the CC has to be greater than a certain number and the CU has to be between a certain number for it to be well graded. If either of those are not the case, then we call it poorly graded. So thinking of that, let's stick around with the USCS and finish this example too. So we have the grain size distribution, which now everyone should be familiar with. So we have our sieve analysis here with our mass retained on each side. And then we are asked to provide the group symbol and the name associated with this. So this is just the raw data. So what we're first going to need to do is interpret this data or make it so we can create a grain size distribution curve. So the sieve size, we have to correspond to the opening size in millimeters. So remember the number 4, the smaller the number, the larger the opening size. So number 4 is 4.7, number 200 is 0.075. And remember that the number 4 distinguishes gravel versus sand, and then the number 200 distinguishes sand versus fines. So everything passing the number 200 is our fine soil. So just by looking at this, how many grams of fines would we have? Yeah, 59.4, right? Because that's how much is past it. So how many grams of gravel would we have? 20.2, yeah, because that's what's above it. So that's all good data, but what we need to plot is the cumulative retained or the cumulative passing. So in order to do that, we would first need to sum up and determine the total amount of material that we pass through our sieves. So that's 1,000 grams. So then we look at it in percentages. So we look at the percentage of mass retained on each individual one. And it's a nice even number because we have 1,000 total grams. So normally it wouldn't just move the decimal place over. But then what we want to look at is the total or the percent cumulative retained. So meaning at the number 200 sieve, 21.12% is greater than it. At the number 200 sieve, 94% is greater than it. So what we want to plot though is the percent passing, which is just 100% minus that retained. So this is how we find our percent gravel, our percent sand, and our percent fines. And so from this, as we'd said before, in percentage wise, our gravel is 2%, our sand is about 92%, and then our fines is 5.9 or about 6%. So right off the bat, like without looking at the flow chart, what do you think that first symbol is going to be? S. Yeah, because the majority of our material is a sand, greater than 50%, 90. So that's right off the bat, we know it's going to be an S. So even though we know that, let's follow our flow chart here, and we see that again that little we said no organics in the title or whatever in the problem statement, so we have no organics there, and then we have the greater than 50% is retained, or sorry, is less than 50% is passing our 200 sieve, so that means we're going to be a coarse grain soil. And then looking at that, which one is greater, number 4, or what is greater, passing number 4 or retained on number 4? Obviously 92 versus 2, so more is passing number 4. So we're on this one here. So now what we look at are these 3 options. And this is looking at our fines. We're seeing, do we have enough fines in our soil where gradation is going to be the controlling factor or plasticity is going to be the controlling factor. So less than 5% fines, 5 to 12% fines, or greater than 12% fines. So we have 6% fines, which would be that middle one. Yeah. So we would have this one here. So this means our soil is either going to be an SPSM or an SWSM. So there's enough fines in there that we use this middle ground of it, but we still have to determine and distinguish this P or W. So what we do is we still have to go through this same step right here, even though it is not on our flow chart because I couldn't fit it. So to distinguish between well graded or poorly graded, we still have to calculate these defining indices for the grain size distribution. So from that grain size, we plot the D60, D10, which is our coefficient of uniformity, and then our coefficient of curvature, which is D30 over or squared times D60 times D10. And this should be part of your lab report. So at least like this is going to be a good practice to do so. But in order to find those values, we need to plot it and then read our grain size distribution curve. So when we plot this, please make sure this is log scale. Every year, there's still a lab report that does not have this in log scale. So make sure that you click and you turn that into log scale so we can read it correctly. But in order for us to read the D60 and the D30 and the D10, so remember that is the diameter corresponding to the percent passing that's on the subscript. So our D60 is going to be, this is 1, 2, 3, 4, 5, 6. So our D60 is going to be equal to, well, I guess 5. What is it? 1, 2, 3, 4, 5. I guess I read that wrong. This should be a 6, I guess, technically. Oh, no. I wrote it the wrong way. Read it the wrong way. So don't do what I just did. So remember, this is increasing this way. So our red value, our D10 is 0.14, and we just kind of interpolate it between using log scale. Our D30 is 0.24, and then our D60, this number is 0.5. So making sure you're reading the tick marks correctly. And remember, these are always going to be interpolated points. The true data are from these bullet points. So it's going to be dependent on the, it's not real data. These bullet points are the real data. So if anytime the line goes in between it, we're technically interpolating it. So that's why we would always say it's about equal to these things. Go away. All right. So we have 3.6 and 8.2. So what we'd want to see is, what do these fall within that range to make it well graded? So our CU is 3.6, and which is less than 6, and our CC is in between 1 and 3. So that means we are poorly graded. So usually what you would check is this: if both of these cases will work, then it becomes well graded. If one of these cases and the other one doesn't, then it is becoming poorly graded. So that means this would be an SP and our soil would be SPSM. So most of the time, geotechnical engineers will just assume poorly graded soil conditions and then do additional testing to see if it's well graded, because well graded soil is not common, I guess. It's harder to find well graded soil, at least here in Florida. I don't know about other states. This would be SPSM. All right, so we're asked to find the entire name now. So we need to go additionally into our secondary little flow charts from the ASTM to find these. So we see the SPSM line right here, and we want to see if it has enough gravel where we have to distinguish that in the title. So does it have greater than or less than 15% gravel? Yeah, less than right here. So it has less than 15% gravel. So what we would call this is just a poorly graded sand with silt. All right, let's look at example 3 here, where are only asked to find the group symbol. Okay, so in this case, we're just given the, and this is a new one. I added this one. This was not on your previous lecture notes from Tuesday. So we're only given the grain size distribution plot. And so learning how to read these is really important. With this, we're also given the fine data, the Atterberg limits. We have our plastic limit of 35% and our natural liquid limit is 30%. So from our grain size distribution, we want to determine what is the percent gravel, what is the percent sand, and what is the percent fines. So percent gravel, percent sand, and percent fines. So our gravel, what we would do is read this point. This is equal to 98% passing. So 100 minus 98 is 2. For our sands, we would look at the 4.7 C down here. And so we'll say this is 20%. So 98 minus 20% is, or 98% minus 20% is 78%. And fines would be 20%. That would be what's passing from there. So with this one, what would be our first letter? Yeah, it'd be S again, because we still have the majority, 78% is our majority. So we would still go through and follow this way here. And then we have greater 50%. So our majority, we know we would have to look here. Now for this one, since we have 20% fines, 20% is greater than 12. So we know we're going to be following here. So since we have 12% fines, we have a sufficient amount of fines where the plasticity will still play a role into our classification. So what we need to do now is look at our Casa Grande chart where we use our liquid limit and we use our plastic index to determine whether those fines are primarily silty or primarily clayey. So first we need to calculate our plastic index. It's a very, very hard equation. It's the plastic limit minus the liquid limit. So our plastic index will be 5%. And we'll do this in 2 weeks to show how you find these values. So we have 5% here. And this chart, though, is going to be rearranged a little bit because we are looking at a sandy soil. And so we only want to determine whether the soil is clayey or silty. So that line is this line here. Even though in the form as it currently is, we distinguish between high plasticity or low plasticity, which is the L or the H. When we're looking at sandy soil, all we care about is that A line. The A line distinguishes between sand or silt and sand. So what this actually looks like, we get rid of all these. What this technically would look like is if it falls within this region, it's going to be silty. If it falls within this region, then it will be clay or an SC. And then we still have that little awkward region right here where we would call it an SMSC. Personally, I've never seen SMSC. I don't know where that geologic formation exists, but it's there for a reason. So it might be there somewhere. So we would do this exactly as we would for the clays, like we saw in our example 1 from last class. So we would first look for our liquid limit. Liquid limit of 30 is down here. And then we would calculate our plastic index. Remember, this y-axis is the index. So that would be somewhere over here, and we would look for where those 2 points intersect. That's going to be a silty material. So the soil would be SM. Now, one of the things that, like, I mean, you can just guarantee will be on the FE, because it's always something that is so easy to mess up, is it, you would plot, instead of the plastic index here, you would put plastic limit, and then boom, you would see that that would be a completely different answer. That would be your clay soil, that'd be SC. And so that's a question I remember they asked me on the FE, and they probably still do today, because it's very easy to mix up plastic index with the plastic limit. But the y-axis is always the index. So you have to subtract those two. So this would be SM soil, which would be a silty fine sand. Any questions on this so far? So the plastic limit, the PL, is a laboratory experiment. And then the liquid limit is a laboratory experiment. So you would get these two numbers from your lab experiment and then just subtract the two to get your index. Now, something to note too with this is on the FE also, like, you might not be able to visually observe. Let's say you have an example where the liquid limit is 60 and then the plastic limit is 30. And you're like, you know, trying to determine, is it over the line? Is it under the line? Luckily, this A line has an equation right here where you might actually have to test it and see where it falls in. You know, just plotting it roughly on a little piece of paper or on a computer screen when you're taking the FE, it might not be as discernible. So you would have to calculate it. All right, our PI is 30. Is that greater than or less than 0.73 times the liquid limit minus 20? If it's greater than, that means it's above the line. If it's less than, that means it's below the line. So you might actually have to do math. I don't know, that's scary. But yeah, just keep that in mind. Hopefully you guys get this by now. Like my exams are meant to model the FE. So anytime I say you might see this on the FE, just, you know, you guys are smart. You understand what I'm saying here. Okay, so I wanted to share some of the examples of some actual data from lab reports. This is a geotech report or borings from a roadway project in Orlando, the Wekiva Parkway, which goes through like the west side of Orlando and stuff. We'll go next week into a little bit more detail of what these lab reports are, how we get this data. This is the profile view of borings. So when they go out with the drill rig, which we'll get a chance to see later in the semester, they drill down in depth, and this is the result where they show it with depth. So at the top right there is the elevation of about 57 feet above elevation. Each one of these little tick marks is 1 foot in depth. So you can see it shows the whole soil profile with depth all the way down to 70 foot below the surface. And this is important for bridge design, for like any type of settlement equations, any type of geotechnical design. So you'll see this is what they'll actually like do. Like the engineer will get the samples in the lab, and then they will do these tests to determine whether it is an SP, an SM, SC, SM, all of these things here. And so this is how we classify it. And the whole reason why we do this is because we have these single discrete points, and they provide the latitude, longitude, location, and all these things. But the goal of classifying is to create like an idealized profile or a typical cross section of what to expect. So you classify soil so you can start looking at similar types of soils and see how they change throughout the profile of our site, you know. So we would look, okay, this is an SM layer right here that is gray, and that's a light gray SM layer. So maybe that's the same geologic formation. This one right here is SPSM, that's some SPSM. So then we can start to create this profile view like this. And then this is usually what you would be handed in your textbook as a student. That'd be like, oh, design a foundation to support like less settlement in this, or design an excavation or something. But all of these nice profiles come from these singular points, which is why we need classification and why we need that universal language, so we can create these profiles and make it understandable through the entire site. So here's another example of soil classification changes, as well as some of the lab data. So this is I think this is over near the Panhandle somewhere. I can't remember where I got this from. So we have data there, and then we also have data right here. And you can see how some of these layers differentiate between them, but then how some of the layers are similar. This little box right here too, this is the lab report data. So that NMC is our natural moisture content, which is our lab one. The negative 200, that's the percent passing the 200s sieve. So sometimes they don't have enough soil or they don't have enough time to do a full sieve stack. They only pass the soil through the 200 sieve to determine what is the percent fine. So this would be a 26% fine soil. And since 26 is between 12 and 50, that means it's an S soil with a either C or an M, and then they did the Atterberg limits to determine it's an SC soil. So you can see this is an example of the needing to do that because soil can change pretty drastically just between the two locations. Okay, so some of the key points from the USCS. This is the primary classification system for soil in the US for any type of just typical geotech report. So any structure, any foundation, any excavation, tunnels, any type of just random like classification, you would be using USCS. It consists of the two letters, so the group symbols, and then this descriptor group name. They classify soil mainly off of two things. So you look at organic and inorganic, and then the inorganics would be caring about the three primary soil grain types, and then the two levels of plasticity, high and low plasticity. And I wanted to highlight these because these are some of the differences when we start looking at AASHTO. The AASHTO method is used for roadway in respect to the ability for the soil to be used as a roadway subgrade or a base layer. So some of these numbers are changed around a little bit. So remember too, this is developed in 1948. We will do an experiment in the class that teaches us, or that is the same experiment that they did back then. It's still the one we do today for liquid limit. And it's not like the most precise experiment at all. But that is still the main way we distinguish between low plasticity and high plasticity. So keep that in mind whenever you are talking to an engineer and they're like, oh no, this is high plasticity soils. We need to do this, 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 and this. Like the test that is defining it as a high plasticity soil is very old and sketchy. So yeah. Good. Yeah. So this is an area that is now starting to be a little bit like empirically based classification. So it's hard like to break down this unified, it took so long to get everybody speaking the same language. And now like a bunch of young engineers are like, well, let's change it all, so it takes a little while. But what we're looking at now is developing different types of techniques based off of the specific use. So like this is a guy right here, Carlos Santamarina. He does a lot of work in looking at a better way for classifying soils. So maybe this is going to be something, that might take hold whenever you guys are senior engineers or, a little bit down the line. So who knows? But there is research in that. But still, the USCS is kind of the standard way of doing it. Okay, the other fun thing about USCS is it's very easy to create like a spreadsheet or automation for it. So since you guys I know are engineering students and don't have any other hobbies, if you want to try to make this as a homework or as like a fun little like assignment. I'm not grading it, but try to see if you can make it as a spreadsheet, and so where you can just input all of these values and then boom, it'll shoot it out automatically, like if you like coding and all that stuff. This is not required at all, but I just think it's fun and it'll help you in the future for it. Huh? This is Excel. Yeah, you can do it all in Excel. It's sketchy, but if you know MATLAB or anything, you can do that. So again, not assigned. If you do show me it and you submit it, then I will be impressed, but that's about all you get. Sorry, unless you really need extra credit, then we can talk. All right, so what we're gonna go over now is the AASHTO. Same ASTM, or sorry, it's still an ASTM, different ASTM. It's 3282, so it's a newer ASTM. And I kind of went over the overview of it last time. What they do is they distinguish the silt, clay, and colloidals by the actual particle size rather than plasticity. So they care a little bit more about the fine content, mainly because what we're talking about for AASHTO is roadway subgrade. And one of the most important things for roadway subgrade is drainage and permeability. So they shift the numbers a little bit for the purpose that they're designing and classifying the soil for. So it's a little bit more highlighted on that. So state highway, it's not safety highway, I had to look that up, but American Association of State Highway and Transportation Officials. This was developed when all the interstates and public roads started booming. So ASTM has a standard, but also AASHTO was like, oh, we can make money too. We're going to make our own standards. So there are AASHTO standards out there too. So it follows both of these. It's basically the same thing. You just have to pay money twice to get it, unless you're a student. So it is a soil rating for roadway subgrade construction. So basically what we're looking at is this AASHTO is a ranking system for the application of roadway construction or the roadway subgrade. So thinking of it as a ranking system, the USCS was not like a ranking system. It was just like, hey, let's all classify the soil for different purposes. But the goal of AASHTO is to read it and then have an understanding right off the bat how applicable or how good this soil will be for roadway subgrade. So it is classified into how many? I don't want to cross it off the whole time. It is classified into 8 groups, primary groups, and then there's several subgroups under it. So A1, there's always going to be an A in front of it for AASHTO. So A1 is the best soil, and then A8 is the worst type of soil. Right off the top of your head, what do you think A1 is?
Clay.
Yeah. Yeah, it's going to be like we want water to be able to drain. We want strength. We want our subgrade for our roadway to stay put, not settle. So it'll be like a sandy soil or something. It's still not going to, it's going to be granular, I guess. And then A8, and I'm sure it's on your notes, so you can just read that. Oh yeah, mucky soil, organic soil, stuff that's going to compress. And that's usually, we wouldn't even use A8. So if you have A soil, then you would do it. Electrostatic is clay. Come on. All right, so granular materials are going to be our A1 through 3. Our silty and clay soils are in between A4 through 7, and then the organic muck is our A8s. So A8 is just like we can't even really use. And then based off of different situations or different roadways, different disciplines, they might say like, okay, we can only accept A1 through A3 soil. So the way they'd classify this again is granular material. This would be like our excellent to good in terms of rating. Our A4 would be our fair to poor, but most of the time they can still make it work. And then A8 is, nope, sorry. So if you got some grandparents or something sitting on a big chunk of land in Florida, and you figure out you have A1 through A3 soil on that land, then the government probably already came knocking, because that's the really good stuff, and that's where they get their borrow pits and all that stuff, and they do the land acquisition to try to get that. But if you have A8 soil and you call the government and be like, hey, I'll sell you my stuff, they wouldn't even care. So this is the ranking system for that. So let's talk about what the numbers actually look like. So we have that first part, A, and then the number. And then we have a second number in some cases to divide it into another subgroup. And then in the parentheses here, we have a group index. So essentially what this whole system is if we have really good material, like an A1 through an A3, then that group number is okay. We don't need to find that anymore. If we have an A, like that second number here, the subgroup, where is it? That subgroup number, that's like, okay, it's on that buffer. We need to define it a little bit more. And then also the group number, that group index in red, this is also like, okay, we still need to define it a little bit more to see if it'll work. Yeah.
What about if we have, say, A6 or A7 starting base? What do we have to do to make this to be able to build on?
I don't know. You could, I don't like it. It could still be used in some cases. It depends on the level of service of the road and everything and the jurisdiction, like who's doing it. Is it a highway? Is it a little city street or something like? The city, well, if it's a highway, then yeah, you probably redesign around it, or you'd have to add a sufficient amount of fill of A1 through 3 material or something. So yeah, this is used in two ways. It's used in like soil classification of what's currently at your site, but it's also used in classifying soil that is fill material to bring to your site. They go both ways for that. So the key differences compared to the USCS, fine versus granule soil. Remember in USCS, we said the 50% majority rule, like which one is the majority? For them, for USCS, the fine versus granule, it's 35%. So if you have less than 35%, like number 200 seed, then it is called granule material. But if you have 35% or greater, then they call that fine material. And the whole purpose is because the fines control the level of permeability. And we want these roadways to be able to drain out and not cause like settlement or ponding or freeze thaw or anything like that. So that's one of the reasons why they care for that added safety of 35% dividing line for fines. The plasticity chart, I don't know why they did this. They're just like, we can't copy the USCS exactly. So instead of 50% liquid limit, they do 40% liquid limit. So the plasticity chart, they still use one. It looks very, very like oddly similar, but they just shifted the liquid limit down 10% to distinguish between clay soils of high plasticity or silty soils of low plasticity. So luckily there is no CU or CC. There's no coefficient of uniformity of coefficient of curvature. Instead, they use this empirical index called the group index. So you still have to find certain passing diameters like we did for the USCS, but you don't calculate CUCC, and I'll show the group index here in a little bit. So this is our flow chart. I made it look like starburst just to prove the colors there of the grading. So we have our A1 and our A1s over here. We have A1A and A1B. Both A1s are like top students, you know, like really, really good. Like they're going to get full ride scholarship as roadway subgrade. And then you kind of move down with ranking here. And of course, A8 is our organic soil that is not used at all. So some of the key differences that you can see again is that liquid limit for high plasticity or low plasticity is 40%. It's not 50%. And I'll show the chart here in a little bit. What you also see is far left, the criteria to become this A1 soil is really high. You have to have less than 15% number passing the number 200, also less than 30% passing the number 40, and less than 50% passing the number 10, and a PI less than 6. So if neither of those are the case, then you bump down to A1B and see if that works. And then if these aren't, then you check these and see if these are the case. If neither of those are the case, then it's probably an A3 or something back. So you have to think of it that way. It's like, do we meet all the criteria to be ranked as an A1B? If not, then we move down along our list. So the other note here too is the granule material. This is 35% is that distinguishing line, where normally this first bifurcation in our flow chart was 50% from the USCS. Yeah.
Why is the A2, A3 at like different spots? Why is it numerically?
Right. So that again, A2, A3.
Like it goes A1, A3, A2, A4.
Oh, I don't know. I'm sure it's written in the words there somewhere. A2. So in this case, A2 and it is usually better workability than A3 because it can be compacted a little bit more. So in CE materials, I don't know if you guys did the optimum moisture content or the maybe that's the geotech one, I can't remember. You do the optimum moisture content, which basically tells you how easily can you compact the soil. So for roadway subgrade, you want soil to be compactable. So you add a little bit of fine material here, and these are better than an A3. So it is kind of weird that they jump over that way, but like you're kind of splitting hairs. In some cases, you would prefer an A3 over an A2. All right, so this is the plasticity chart for AASHTO. It looks very similar, but again, that liquid limit is 40 right here and not 50. And then there is a line here of 10 plasticity index that distinguishes it between like a silty soil or a clay soil. So it's a little bit easier to read there. The only line that you have to worry about to distinguish A27s and A7s or A75s and A76s is that this one right here. Everything else, it's just these different quadrants. But you would read it exactly the same, the liquid limit, and then of course this is the plastic index, which is the plastic limit minus the liquid limit. So same thing as before, really important to calculate that and not just use the plastic limit. So just to compare again, this is the Atterberg chart for the USCS. So you can see very similar options there. And this is going to be something that is like going to be provided on your FE handbook, and you have to make sure you're reading the correct one, like when you're going in between the two. Okay, so let's talk about the group index. This is an empirical equation. So this is based off of observations and data fitting rather than theory or analytics or anything. So the index relates the quality of soil as a subgrade. So if we have some of these top tier soils, so any of them in the green where you have A1s, A2s, or A3s, then we do not need a group index. The group index is 0. So we only need a group index to further define and see if it's acceptable if we have an A26 or A27 or anything else. So if we have an A26 or A27, we use this empirical equation. And this F is the percent passing the 200 seeds. PI is plastic index. And then anything else that is not on here, then we use this larger, gnarly looking group index equation. So in general, as the group index goes down, so the smaller the number of the group index, the better the quality is. So I'm going to show an example like on the next page, but like some states will have set like criteria where like if we have a group index of 15 or greater, then we can't use the soil at all. You know, it's again, it's dependent on the jurisdiction, the use of the soil, and that kind of thing. So some of the rules here, if the GI is negative, so if you calculate GI being negative, then we just say that this is 0. Group index is also always rounded to the nearest whole number. So we don't show decimal places. We just find like round to the nearest whole number, not necessarily round up. There's technically no upper limit for GI. So it's 0 is the best, and then we keep going up and we can go higher. And then also in general, again, just as like a general rule of thumb, but some jurisdictions will say differently. If you have a group index greater than 20, this indicates very poor subgrade. So the reason we use group index primarily is comparing like the same soil classification. So we would look for it in the same group number, like only in the same group number. So let's say we have an A27 from like this person's land and an A27 from another person's land. So they both classify as A27s. Which one are we going to use as fill material for our roadway? Whichever one has the lowest group index. So that would be the deciding thing. We would still allow the original primary ranking system to take precedent, where if we had like an A2 whatever over, that initial thing, the initial like ranking system would be priority. So let's look at an example with AASHTO. So we have our sieve analysis. We need a little bit more data now. So we have our 10, our 40, and our 20 passing. And so this 6% passing, remember that distinguishing now is whether it's greater than or less than 35%. So it's less than 35%. So that means it'll be primarily granule, which is good. So we follow this. So now we want to see, is it less than, I guess I skipped forward that. We know it's less than 35%, but is it also less than 25%? Yes, it's 6% passing. This is our example. So yes, it's less than 25%. So now what we want to do is we take the liquid limit and the plastic limit on our number 40 sieve. So we're told that it's non-plastic, so it is, the PI is 0. So since the PI is 0, we would look, do we have less than 50% passing our number 40 sieve? Yes, because this is less than 50%. And so we would see which one is applicable here. So do we have less than 15% passing our number 200 sieve? Yes, because we have 6. Do we have less than 30% passing our number 20 sieve? Or 40 sieve? Yes, because we have 28. And then do we have less than 50% passing our number 10 sieve? Yes, because we have 48. So boom, it's checking all the boxes. We also have a plastic index less than 6 because it's 0. So yes, it gets the highest grade, A1, 8, which is really good. And then for the GI, what would we calculate for the GI? Yeah, exactly. The GI in this case, since it's the highest grade, we don't have to worry about additional testing. We just let it go on its own, and it's an GI of 0. So the technical form would be the AASHTO classification be A1A 0, which I have never seen in the real world. We never really have this in Florida. Yeah, if you do, then it's already bought by Argos or CEMEX or somebody to use as concrete sand or something. So yeah, most natural soil will not be this. All right, another example here, and since we have more data, we probably know it's going to be a little bit harder. So we have this full passing, and then we also have our Atterberg limits down here. So we have number 200 passing is going to be 35%. So we're still granule material because 34 is less than 35, just barely. So this is going to be granule material. So that means we're going to be going this way still. So that's nice. And then we have to look, is it less than 25% or just less than 35%? Remember, it's 34% passing, which means we go this way. So it's greater than 25 and less than 35. So, then 35, it's 35 or less. So yeah, you would go to the left still. So if it was exactly 25, you would still go to the left because it says less than 35. If it said 25, or sorry, on the right hand, if it said 25 or less, then it would be. And for this one too, I would recommend looking at the AASHTO like standard, because they like USCS one, they have a flow chart exactly like mine. If you don't like flow charts though, the AASHTO has a different, it's more of a table format with a little bit more like an if kind of thing. Like if you do this and this and that kind of thing, kind of highlights the ranking a little bit better, but I just like looking at flow charts. It's easier for my brain. That might not be the case for you. So look through the AASHTO and the ASTM associated with this. and it might help click a little bit more seeing it in a different light. Okay, so in this case, we are going to go through this center one here. Oh, spoiler alert, sorry, I went a little too far. So yeah, we'll go through here. Is our PI greater than 11 or less than 10? So is it going to be 10 or silty? Yeah, so our PI is going to be 49 minus 37, which is 12. So it's going to be primarily clay. And then we look at our liquid limit. Is it less than 40 or greater than 41? Yeah, so we're 37, so less, so it'll be an A26. Now, when we have an A26, we have to still calculate the group number or the group index. So with that group index, we have to make sure we're choosing the right one. So we're going to be doing 0.01 times F200. So this F200, this is percentage passing the 200 or the fine fraction. And this is in percentage format, which can be a little confusing. So you would percent passing the 200C, but it's in percentage form. So that would be this number here. So we keep it in percent, 34% minus 15. And then our plastic index, again, we calculated before. Is 12. So our group index is 0.38, which would equate to what group index?
0.
Yeah, it's still close enough to 0, so we would call this to 0. But remember, we would only use this group index, like we still show the group index to our client and stuff, just in case they need it later in the future. But we would only use this group index if we are comparing another A26 or another A27. Like we would not use this group index if we are comparing it to like an A5 or an A4, because this A2 is in its own category. Okay, let's see. So our AASHTO classification, yeah, it should be 0. I don't know why my font got messed up and it's not at the bottom of the screen. All right, I think I have one more example. Yeah, one more example. So we have our sieve analysis and we have our plasticity again. So again, those are the important ones. We're going to do the same thing as before, but now we have greater than 35% passing. So we know it's going to be far left, and we have a plastic index of 12. So with this one, we know we're going to be going this way this time. We're greater than 35%. So we're just going to get rid of this here. So let's see what we have again. Our plastic index is 12, which means we are going to go this way. And then our liquid limit is 43, which means we're going to go this way. And so now what we're asked to do is check the plasticity chart to determine whether it's an A76 or an A75. So we need to make sure we're looking at the correct plasticity chart. The government one, not Casa Grande, not the private Casa Grande one, the government one that looks oddly like Casa Grande's. And this one is following the liquid limit and the plastic index, same as before. So let's just plot it here. So 43, let's say that's like right here, and our plastic index is 12, which should say is right here. So again, if we try to visualize this, going to be kind of hard to see exactly where that is. So what we are going to do is use this equation to distinguish whether it's an A75 or an A76. So our plastic index is either going to be greater than or less than liquid limit minus 30. That's what that function is saying. So our plastic index is 12. Liquid limit minus 30 is 13. So our plastic index is less than 13 or less than that function. So that would mean we are going to be below it, below the line, and we would be an A75. Okay, and what we have to do now, we still have to find our group index. So we know it's not this, we know it's not this. So now we need to use this larger equation here. So just be very careful plugging everything in. correctly. We have 62% as our F200. And then obviously our liquid limit and our plastic index is also shown in there. So our GI in this case is 6.75, whatever, which is going to round up to 7. So the classification would be A75, group index of 7. Cool. You guys all get a Duolingo badge now speaking AASHTO and USCS. So add that to your bilingual LinkedIn thing. All right, so the key points to AASHTO. It consists of the group number plus this group index. And again, it's always geared towards, is the soil good for roadway subgrade? So conceptually, is an A2 soil better than, or sorry, is like an A1 soil better than an A7 soil? You know, like knowing, like just by seeing the classification, you have some engineering significance to it. So we have our A1 through A3, A4, A7, organic soils, A8s. Anytime you have that, even if it's in a pond design, you just remove it basically. The questions is 35% passing the 200 sieve? Yes and no. Remember AASHTO or USCS, that question would be 50% passing. So they're a little bit more like, what's the majority? And AASHTO is a little bit more direct with 35%. Yes, A1 through A3 is less than 50% or 35%. Everything else is greater than 35%. Yeah, and then silty and clay, to distinguish between that, you would look at this plasticity chart rather than the Casa Grande plasticity chart. So we have a PI of 10 is clay or silty, and then the liquid limit high/low plasticity is 40 instead of 50. So they're very similar in some cases, just shifted a little bit. That would always be provided. The chart would always be provided to you.
The flow chart?
No, these charts right here. The plasticity charts. Yeah, and then A8 similar would be like visual for organic peat and muck and all that stuff. So here's some like general typical soils, like comparison, like overlap between them that will help. But since they're different classification systems, you can't compare like apples to apples. But generally, like your A1s are going to be the gravelly soils. Your A1As are going to be more of the gravelly soils. Your SMs and your SCs are going to be like your A24, A26s, A27s. And then your primarily silts or primarily clays, so your Ms and your Cs for your group indexes will be more so the A4, A6s, and A7s. So this, ignore all this crap, just kind of look at the distinguishing here. So we have primarily gravels, primarily sands, and then the rest of it here. So you can kind of see that sense here. But again, they're different purposes. So it's not always like comparable apples to apples. Okay. You guys want to review this in chance now or no? You want your exams back? Is it better on a Thursday? All right, so we're gonna hand back the exams. Also, sorry for everybody watching at home who didn't come to class, but I'm not recording this, so